Okay, let us do the second sorting algorithm, which is called the insertion sort. So insertion sort is again a very commonly used algorithm, and again kind of like we maintain the unsorted and sorted portion in the bubble sort. We'll maintain a similar thing here for insertion sort. So let's try to understand insertion sort using this example here. Now, in the case of bubble sort, the unsorted portion was first followed by the sorted portion. Whereas in insertion sort, it's the other way around. One sec. The sorted portion is first followed by unsorted portion. So let us consider in some iteration that we are going through insertion sort. This is how the array looks like, and again we can do everything like in the bubble sort on the input array itself. There's no separate memory location address block needed. So this is, say, the sorted portion that we have processed, so that we have accomplished so far, and this is the unsorted portion. So in the next iteration that we are going to go through the steps, what we have to do is we have to pick the first element in the unsorted portion, which is in this case the element at index 5. That's the first element in the unsorted portion for that iteration, and insert that element somewhere in the sorted portion, so that at the end of that iteration the size of the sorted portion increases by 1 and the size of the unsorted portion is shrinking by 1, such that the elements in the sorted portion still stay sorted. So that can happen only if 30 is inserted in between 20 and 32 here, so that the sorted portion will look something like this: 12 followed by 20 followed by 30 followed by 32 and then 37, 45, and the unsorted portion is 8 and 9. Okay, so how we accomplish this? How are we able to insert the first element in the unsorted portion to its appropriate location inside the sorted portion, so that the size of the sorted portion increases by 1 at the end of that iteration and it is still stays sorted? And if we can do that for every iteration, we sort the entire array. Okay, so to begin with, we can say the for a given array like this, the first element forms the sorted portion, the rest of the element will form the unsorted portion. So we can, the first iteration, try to insert the first element in the unsorted portion, which is this 23, somewhere in the sorted portion, so that after that iteration the sorted portion expands by 1 element, becomes sorted, stays sorted 23, 45, and then the rest of the elements. And we'll do that in the other second iteration. The 8 is the first element of the unsorted portion, and try to insert it at the appropriate location, so that the sorted portion increases by 1, so 8, 23, 45, and the rest is the unsorted portion. And we do that for all the iterations and the array will be sorted. So the key thing in this algorithm is how to figure out, as I mentioned here, where to insert in the sorted portion. Okay, alright, so that's what we are going to see now as an example, and then we'll look at the pseudo code. So let us refer to the element in the okay, so the I index always runs through the unsorted portion. So to begin with, as I said, we can consider the element at index 0 to be the sorted portion, and the unsorted portion really then starts from index I equals 1. So that's why in the pseudo code we'll see the index I running from 1 to n minus 1, because that's really the unsorted portion. The element at index I equals 0, not I equals 0, the element at index 0 could be considered to be part of the sorted portion. So the index I will really run from 1 to n minus 1, that's an unsorted portion. And after we go through the first iteration, as you see here, the unsorted portion is really now starting from index 2. So that's why I will be 2 for that iteration number 2. Then at the end of that iteration, the unsorted portion really starts from 3. And for iteration 3, I equals 3. That's the unsorted portion to begin with. So in the ith iteration, the value of I will be the first element in the unsorted portion. So in the iteration I equals 1, the value of I is the first element in the unsorted portion, which is 23. Iteration 2, the value of I is the first element in the unsorted portion, that is element 8. Similarly, iteration 3, the value of I, which is index I, and the element there is the first element in the unsorted portion, which is 12. So I am capturing that value at index I, which is the first element in the unsorted portion, in a temporary variable, say v. And you will see soon why we need to store that value of the first element in the unsorted portion in a temporary variable. Okay, so let us use a temporary variable v to store the value of the first element in the unsorted portion. So that's basically the element at index I. Okay, so in this iteration, I is 5, and the value of the element there is 30. Alright, so everything before that will form the sorted portion. So if that will run from index I minus 1 to 0. So as you see, I is the index of the first index of the first element in the unsorted portion. Then everything before that is the sorted portion, so that will run from index I minus 1. If you look in the backward reverse direction, I minus 1 all the way to 0. So we'll run a J loop now inside that sorted portion in the backwards reverse direction, starting from index I minus 1 to 0. Okay, so what we do now is, for every value of the elements at index j, we compare them with the value of this v, which is 30 in this example here. So let us do that. So at index j equals 4, the element there is 45. 45 compared with 30. Now you see the value of the element at index j, we can call it as a of j, is greater than 30. So that means we have 45 here in the sorted portion, and there is a value that is less than 45, or less than or equal to 45. So simply put it, 45 is greater than 30. That means 45 is greater than something to the right of it, as it is in the array. That means that's not the final position of 45 in the final sorted array, because we have something less than or equal to 45 to the right of 45. Right? So what we'll do is, we will copy the value of this 45 to its right. So if we find a of j to be greater than v, we will copy the value of a of j to its right. So that's what we do. If a of j is greater than v, a of j plus 1 equals a of j. So if this is j plus 1 is the next index, we'll copy the value of a of j to a of j plus 1. So that's why we copy 45 to its right. So you see the value of index at index I could get overwritten if this is a scenario. So we are going to lose that 30. So in order to have a copy of that value at index I, we save it to a temporary variable. So then just move the j index to the left. So j is now at index 3, the value there is 37. So again compare the 37 with the 30. So again you see something less than 37 is to the right of 37. That cannot be the case. So that means 37 is not in its final position in the sorted array. So make a copy of 37 to its right. So 37 is copied to the value to the right, and move the j further to the left. So j minus minus. So then j comes to index 2. The element there is 32. So 32 compared to 30. So again 32 is greater than 30. So copy 32 to its right and move j further to the left. We have 20 there. Now 20 is not greater than 30. So remember, this is the sorted portion. If 20 is not greater than 30, that means 20 is less than 30 or equal to 30. So anything to the left of 20 is also going to be less than 30, because this is the sorted portion. So if 20 is less than 30, anything to the left of 20 is also going to be less than 30, like 12 is less than 30, and so on. So that means we can stop our j loop right there. We don't have to go all the way to the left. So once we decide to stop the j loop at that index, that means we have really found where to insert that v. So we are at where a of j is less than or equal to 30, the v. So we can insert v to the right of that j. That means we'll insert v at j plus 1. So we can set, after we exit this j loop, we set a of j plus 1 to be equal to that v, which is 30. So 30 gets inserted here. So we had 32 there, right? So the 32 will get overwritten with this 30. I don't need to worry about losing the value of 32, because we would have already copied the value of 32 to its right as part of the process. So we are not going to lose any value. Okay, so at the end of this iteration, the ith iteration, the size of the sorted portion is increasing by 1, and it still says sorted, and we'll just repeat this process in every iteration. Okay, let me check how much time we have. Right, so let us go through the pseudo code, and as part of that we'll look at the example one more time. Any questions? I think it's better if there are any questions, just wait and look at the pseudo code, and that will really clarify things if you had any questions. Alright, so as I said, if you are given the array from index 0 to n minus 1, to begin with, we'll say the index 0 is the sorted portion, index 1 to n minus 1 is the unsorted portion. So the I loop will really run through the unsorted portion. So we'll run from index I equals 1 to n minus 1. And for each iteration of the ith loop, we'll run this j loop inside. So in a particular ith iteration, the value of I, so to begin with I equals 1, that represents the index of the first element in the unsorted portion. And we store that also in a temporary variable v, the value of that element at that index I. So now we are going to run the j loop from index I minus 1 to 0. So why I say I minus 1 to 0? Because I is the index of the first element in the unsorted portion. So everything before that is the sorted portion. So that will run from index I minus 1 all the way to 0. So that is why we start the j loop from I minus 1. So the j loop always runs through the sorted portion in the reverse order. So j equals I minus 1 to begin with, and we run the j loop as long as it is greater than or equal to 0, because we cannot run if j becomes less than 0. The loop index cannot become negative. So since we need the value of j after we come out of the j loop, that's why for implementation purposes it's better to implement using a while loop for the j loop. That's why I show here the while loop. So j equals I minus 1 to begin with, and run the j loop until it is greater than or equal to 0. So now what we do inside the j loop, we are comparing the element at index j to the value v. So if a of j, which is in this case 45, is greater than 30, which is v, we make a copy of that element 45 to its right. So that means we make a copy of a of j to j plus 1. And that is done if a of j is greater than v. So if a of j is less than or equal to v, right? So like in this case, a of j is 20, less than or equal to v, which is 30, and that's the time we break from the j loop. So that's what I show here. If a of j is less than or equal to v, that is same as telling v greater than or equal to a of j, both mean the same. A of j less than or equal to v is same as telling v of v greater than or equal to a of j. We break from the j loop. And when we break from the j loop, this is the j loop starting with the while and end while, and what we do, we write at j plus 1, a of j plus 1 equals this v, which is the 30. So that's why even when we come out of the j loop, we need the value of j. So it's better to run a while loop for implementation with j initialized before outside the while loop with I minus 1, so that we can have the scope of j is visible outside the j loop, the while loop. So we can set a of j plus 1 equals v. And this is when after we break from the j loop. Now if a of j is greater than v, like this 45 greater than v, which is 30, then all we do is simply copy the value of a of j to index j plus 1. So we set a of j plus 1 equals a of j, and then we decrement j, move j to the left, j minus minus, and now j at index 3, again compare the value of a of j with v equals 30. So 37 is greater than 30, satisfies this condition. So we can move copy 30 to its right. So we're not moving, we're just copying 30 to its right at j plus 1, and keep going through the process until we come across a j where a of j is less than or equal to v, like this 20 here. So when we come across such a j, we can stop, because as I said, this is the sorted portion in which you're running the j loop. So at this index j, a of j is less than or equal to v, means anything to the left of this j will also be less than or equal to this v. So we don't really need to move all the j loop all the way to the left. And that's the pseudo code. Okay, any question? Right, so yes.
Yeah, I think my question is, why are we using the greater than? Because I thought why are we using the greater than or equal to symbol in that if statement right there?
Okay, so look at this example here. So a of j is 45, right? So if 45 is greater than 30, that means this is not the final position of 45, because 30 was picked something to the right of 45, and we see 45 to be greater than that element. So we have to make a copy of 45 to its right and then move to the left, isn't it? So a of j greater than v really corresponds to copying the value of a of j to its right at index j plus 1. The other possibility is a of j what? Less than or equal to v, isn't it? If this is one scenario, the other scenario will be the opposite of this, a of j less than or equal to v, which is this. Is that easy to visualize? It's the same thing.
Yeah.
So I could write it like this. I wrote it as an image file, that's why I could not change it. I think it's the same thing. We can write like this: index j equals I minus 1, run the while loop from j until j greater than equal to 0, and I think this will make it even clear. If a of j greater than v, then copy a of j to its right. Let me see, and else what? Break the j loop. So both are the same. So else means what? A of j less than or equal to v. Okay, and then end if, and while, and then outside you write a of j plus 1 equals v. Now this equal to thing occurs for scenarios like this. So for example, if we have an array like this, let me go back here. So if you have 12, 20, let us say you have 30, 30, 45, and that's the sorted portion. So let me highlight that. Let's say the sorted portion. And then you have the unsorted portion with this 30. So let me get back to the black color. So now you're trying to insert this 30. So you see what will happen. This is our j at this index. So a of j is 45, right? So 45 is greater than our v, which is this 30. So what would you do? You would move 45 to its right. Not move, copy. So v is stored in a temporary variable as 30. Then this will be 45. And then your j will be right here. Then compare a of j, which is 30, with this 30. So you see now this 30 is less than or equal to 30, this v, right? So really don't have to keep moving all the way to the other 30s and then insert that j, that v here. You can stop right here and break the loop and insert this or override this index at j plus 1 with our 30, which comes from this v. You see that? So that's why we have this less than or equal to, or in this case greater than equal to, whereas in the pseudo code which I wrote it earlier, this is less than or equal to. The same thing. This is a of j less than or equal to v, the same thing, but I wrote it as b of greater than equal to a of j. You understand?
Yeah, I understand.
Okay. Any other question?
No, sir.
Alright, so let me see, what time is it? Okay. So let us just go through the best case, maybe the worst case next time. So when can we have the best case? So the best case is if the array is actually sorted in this forward order that we really want to sort it to. So if the array is sorted in the forward order, let us see how much time it takes. So if it is 12, 20, 30, 45, some 60, then 70, like this. Then to begin with, what we'll have is this is the sorted portion, and the rest is the unsorted portion. So in the first iteration, what we'll do, we compare the first element, the unsorted portion, to its left, and you see this a of j is less than v. So we simply break from the loop and write that a of j plus 1 equals v. So that means at the same location where we picked our v, we will overwrite 20 with 20 and say that the sorted portion has expanded by one element. So this is 12 and 20. So how many comparisons we did inside the j loop? Just one comparison, right? Because we started with that j and we really didn't move further to the left. Similarly here, we start with this j at index 1 and our I is index 2, and we compare a of j with the element at index which is v, which is 30, and right away a of j is less than v. So we really don't have to move to the left. We break from the j loop and overwrite 30 with 30. That's a of j plus 1 with v. So at the end of that iteration, we will say the array sorted portion has increased by one element, like this. So basically you notice in the best case, the J loop is run with only one comparison of comparing A of J with V, and right there we'll see A of J to be less than or equal to V, and we can stop the loop, break the loop. Is that clear? So the best case is running the J loop only once, or doing only one comparison inside the J loop. That's better to put it like that. So doing only one comparison inside the J loop for each iteration of the ith loop. So if you write this as a summation for the best case, it will look like this. So the I loop will still run from I equals 1 to n minus 1, and you really have a J loop, but the J loop is running only for with only one comparison, right? That is comparing A of J with V, and we stop right there, and J is I minus 1, right? So J is I minus 1, and we just do the comparison of A of J with V, and we stop and don't move further to the left. So the J loop runs with only one comparison needed for each iteration of the index I, and that's the summation we need to solve. And this is again following the upper limit lower limit format. So a constant inside, so that's the upper limit minus the lower limit plus 1, which is simply n minus 1. So that is the best case number of comparisons we do for insertion sort, n minus 1 comparisons. So since we saw this in detail, I encourage you to go and look at the worst case, the math involved in the worst case, and also something called the average case and the math involved there. So we'll come back and work on them and move on to the next thing. Okay, and you should know how to solve this double summation based on the previous examples you have seen. Okay, so we'll stop with this and meet on Thursday. Let me take the attendance, don't log out.